When computers were first invented, there was only one brain, the CPU. It handled everything, every calculation, every instruction, every decision a computer made. Early computers had no choice. Memory was slow, hardware was expensive, software was simple. The CPU had to be a master of everything. For decades, that model worked. Engineers made CPUs faster. They increased clock speeds. They added instruction pipelines. They introduced multi-core designs. They shrank transistors again and again. Each generation delivered real progress. Software evolved alongside hardware. Operating systems became more advanced. Applications became richer. Computers transformed entire industries. But then computing changed. Not slowly, not gradually, fundamentally. Modern workloads stopped behaving like traditional programs. Instead of executing instructions one after another, computers were suddenly asked to process massive amounts of data at the same time. Images, video, search engines, recommendation systems, neural networks. And quietly, without most people noticing, CPUs started falling behind. Not because they were poorly engineered, but because the problem itself had changed. Today, the most advanced computers on Earth no longer rely on CPUs to do the heavy thinking. They rely on AI chips. And this shift is not a performance upgrade. It's a complete redesign of computing itself. Number 1. What CPUs were designed for? The CPU is a general-purpose processor. That means it is designed to do many different things reasonably well, rather than one thing extremely well. Its greatest strength is flexibility. It can run operating systems, handle interrupts, manage memory, schedule tasks, execute complex logic. CPUs are built around control flow. They excel at making decisions, if statements, loops, branches, exceptions. This makes CPUs perfect for user interfaces, databases, operating systems, networking, control systems. But control logic is expensive. A modern CPU contains branch predictors, out-of-order execution units, speculative execution engines, deep instruction pipelines. All of this hardware exists just to keep the CPU busy, and all of it consumes power. For traditional software, this overhead is acceptable. For AI workloads, it becomes a massive inefficiency. Number 2. Why modern workloads broke the CPU model? AI does not behave like traditional software. A neural network does not make decisions line by line. It applies the same mathematical operation to huge blocks of data, over and over again. Matrix multiplication. Tens of thousands of values multiplied and summed simultaneously. There is almost no branching. Almost no conditional logic, almost no instruction variation. CPUs are optimized for changing instructions quickly. AI needs unchanging instructions applied everywhere. This mismatch creates waste. The CPU keeps asking, what should I do next? AI keeps answering, do the same thing again. Trying to run modern AI on CPUs is like using a multi-tool to dig a tunnel. It works, but it wastes time, energy, and resources. Number 3. The fundamental limitation of CPUs. The biggest enemy of modern computing is not speed, it's data movement. Every time data moves from memory to a processor, energy is consumed. Every cache miss costs power. Every memory fetch adds latency. This is known as the memory wall. AI workloads hit this wall constantly. Large models don't fit in cache. They stream data endlessly from memory. CPUs were never designed for this. As models scale, CPUs hit a point where more power does not mean more performance. More heat does not mean more speed. More cores do not solve the problem. This is a physical limit, not a software bug. Number 4. What AI chips do differently? AI chips flip the design philosophy. Instead of optimizing for control, they optimize for throughput. Instead of a few complex cores, they use thousands of simple compute units. Each unit does one thing: multiply, accumulate, repeat. AI chips minimize instruction overhead. They remove branch predictors, complex schedulers, speculative execution. They replace them with dense math units, wide data paths, local memory. Data stays close to computation. This single change delivers enormous benefits. Less data movement, lower power consumption, higher performance per watt. AI chips are not smart, they are efficient. Number 5. GPUs were the first warning sign. GPUs were never meant to run AI. They were built to draw pixels. But graphics rendering is inherently parallel. Every pixel can be processed independently. When researchers realized neural networks had the same structure, GPUs became accidental AI accelerators. This was the first sign that the CPU era was ending. Gaming hardware began outperforming supercomputers in AI tasks. That should have been alarming. Software ecosystems followed. CUDA transformed GPUs into compute platforms, but GPUs were still general enough to carry unnecessary features. They were a stepping stone, not the final solution. Number 6. The rise of dedicated AI chips. The next step was specialization. Companies stopped adapting old hardware. They built new hardware. Chips that did one thing extremely well. Google's TPUs removed everything unrelated to neural networks. Apple's neural engines optimized on-device AI. NVIDIA's tensor cores accelerated matrix math directly in silicon. These chips didn't try to be flexible. They tried to be efficient. The result was transformative. AI models that once took weeks to train now took days. Inference that once required servers could run on mobile devices. This was not optimization, it was reinvention. Number 7. Power, heat, and economics. AI is not limited by algorithms. It is limited by electricity. Data centers are reaching power ceilings. Some facilities cannot expand because there is no more electrical capacity. Cooling systems are maxed out. Infrastructure costs are exploding. AI chips allow more computation per watt. That makes them economically mandatory. Without AI chips, large-scale AI becomes financially impossible. This is why every major data center operator is investing in accelerators. Number 8. Why CPUs are not disappearing. Despite everything, CPUs remain essential. They are the conductors. They orchestrate systems. They decide what runs where and when. AI chips cannot boot computers. They cannot run operating systems. They cannot manage resources. They need CPUs. Modern systems are becoming heterogeneous. Different processors for different roles. This is not a temporary phase. It is the new normal. Number 9. The new computing stack. Computing is no longer about one processor. It's about systems, CPU, GPU, AI accelerator, memory hierarchy. Software must adapt. Developers must think in parallel. Architects must think in power budgets, in specialization. This changes education, tooling, and design philosophy. Number 10. What this means for the future. AI chips reshape power in computing. They are expensive to design, difficult to manufacture, dependent on cutting-edge fabs. Only a few companies can build them. That concentrates influence. The future of computing will not be decided by software alone. It will be decided by silicon. Final reality CPUs are not failing. They are being surpassed by specialization. AI chips are not replacing CPUs. They are replacing the idea that one chip should do everything. Computing is becoming modular, purpose-built, efficient, and irreversible. Once hardware evolves, software follows. And once specialization begins, there is no going back. Now tell me in the comments, do you think AI chips will eventually dominate all computing? Or will CPUs evolve and reclaim their role? And make sure to subscribe, because the future of computing is being rewritten in silicon.